Gnanam paramam dheyam. Knowledge is supreme.
We will continue on our discussion of character tables. We have started from this great orthogonality theorem which we have not derived, but we explained that for irreducible representations the elements of the transformation matrices behave like a set of orthonormal vectors. Okay? That is what the great orthogonality theorem translates to. And what is really useful for us and something that we will need to remember if you want to derive character tables and also otherwise is we need to remember that there are 5 important rules that come out as a result of great orthogonality theorem. And these rules actually answer some of the questions that we have been asking. How many irreducible representations are there for a given point group? The answer is number of irreducible representations is equal to number of classes. What is a class? If I bypass group theory, the answer is a class is symmetry operations in a class are equivalent to each other, like the 3 sigma v's in C3V, they belong to the same class. Like C3 and C3 square operation, again in C3V, they belong to the same class. Using these rules, you might remember we derived the character table first for C2V, okay. I will just go through it quickly. And for C2V, what we found was that we are going to have only one dimensional representations, and so the characters can be only either +1 or -1, cannot be anything else. Because if it is a one dimensional representation, then in response to any symmetry operation, a function can either remain itself or it can change sign. It cannot become 5 times itself, it cannot become 0. So, other than 1 and -1 you cannot get anything else, alright. And then we worked out the bases as well, and what is not written here is Rx, Ry, Rz. Did we work out Rx, Ry, Rz on the board? We did not do it, right, we can do it now, or maybe we will do it when we show you the entire character table. And then we said that these irreducible representations essentially tell you how these functions behave as a consequence of each of the symmetry operations. So, if you take Z, it is totally symmetric in C2V. No matter which symmetry operation you use, Z remains Z, it does not change. If you take X, it is symmetric with respect to E, antisymmetric with respect to C2, symmetric with respect to sigma V, antisymmetric with respect to sigma V dashed. So, this, if you want to know the overall behavior of a function in response to symmetry operations, you have to look at the entire collection of characters, which is the representation. So, another name of representation is also symmetry species. The symmetry species denotes how the functions behave as a function of the symmetry operations, we are repeating ourselves. And then we talked briefly about Mulliken symbols, and there we said that if it is one dimensional, then you either call it A or call it B. A if the character for the principal axis of symmetry is 1, B if it is -1. And then we said that if you now take perpendicular C2s or sigma V's, and if the character is plus or -1, that tells you which subscript to use, 1 or 2. And so that way we arrived at the names of the symmetry species A1, A2, B1 and B2. Now, what we have not talked about so far is sigma H. We are going to show you some examples. Wherever there is a horizontal plane of symmetry, if you have a one dimensional representation which is symmetric with respect to sigma H, then you use a dash, where if the character is +1, and if it is antisymmetric, character is -1, then you use a double dash. We will show you examples shortly. And if I is there, then it is very simple. What do you call functions that are symmetric with respect to inversion? This is something we have not discussed so far. What do you call Yeah, Raksha, symmetric with respect to inversion. Another name, even function, okay. Another name, simple name, something that you have used many times. Gerade, that is right, Gerade functions. G, remember that G functions, U functions, bonding orbital, anti-bonding orbital, right. So, if it is +1, then you call it, then you use the subscript G. If it is antisymmetric, then you use the subscript U, okay. And as you will see, in groups of high symmetry, sometimes it is not necessary to use that dash, double dash. Many times we omit designations that are not required, okay. And this is something I told you already. If it is 2-dimensional representation, you use the letter E. 3-dimensional representation, you use the letter T. Now see, if I have a 2-dimensional representation which is antisymmetric with respect to say perpendicular V, what should I call it? A 2-dimensional representation E, antisymmetric with respect to sigma V or a perpendicular C2. What should the name be? Yeah. So, what should it be completely? I heard the right answer, but the whole thing, it is E anyway, and you have to use the subscript 2. So, which symmetry species is it? E2, right. Now, let us say that a center of inversion is also there, and this 2-dimensional representation we are talking about is symmetric with respect to inversion. It is E2 already, over and above it is symmetric with respect to inversion. What will the name be? E2G? Does that ring a bell? Have you heard this term E2G anywhere? Where? Octahedral? Octahedral, yeah. So, in octahedral complexes, you say that d orbitals split into 2 groups, one is EG, the other is T2G. Now, look at this thing, T. T is a 3-dimensional representation, right. So, in 3-dimensional representation, if it is symmetric, antisymmetric with respect to sigma V or perpendicular C2, it becomes T2, and if it is symmetric with respect to inversion, then it becomes T2G. So, this EG and T2G, these names that you have learned from maybe class 11 or class 12, they actually come from this symmetry of wave functions. So, in the second part of our discussion today, we are going to talk about symmetries of wave functions as well. Okay. So, this is your homework. Then C3V we have, and here for the first time we encountered a 2-dimensional irreducible representation, E in this case. Now, the question that we want to ask is, what is the meaning of -1? What is the meaning of 0? Okay. I think we asked that question, but we did not answer earlier. To do that, let us look at the basis. I am telling you that x and y jointly form the basis for E, right. So, to understand the meaning of -1 and 0 here, what we should do is, we should work out the transformation matrices for E. Well, E as in E irreducible representation, what is the transformation matrix for the identity operation E? Yeah, 1 0 0 1, that is very simple. What is it for, okay, let us do sigma V first. What will it be for sigma V? Of course, I can take sigma V anywhere, right, and what is the basis we are using? We are using the basis xy. So, let us take I mean any sigma V, it does not matter. The only thing that we have to remember that your C3 axis is Z. So, the plane that you take sigma V must contain Z in it, right. So, our discussion becomes simpler if we take xz or yz plane, or you can take anything in between, but the point is your Z must be contained in that plane. Are we clear about that? The sigma V, it must contain the principal axis of symmetry, which by definition here is along Z. Let us use sigma V Zx. So, if I use sigma v zx, what happens to x, what happens to y, what is x dashed, what is y dashed? Zx, maybe I will draw it. This is x, this is y. What happens when I apply sigma zx to on zx? Does it change? Does it? So, it remains x, right? It remains x. What happens to y? Y becomes minus y, very simple. What is the matrix? Yeah, 1 0 0 minus 1. It is not very difficult to see that the same thing will happen if I use sigma yz, right. Okay. Suppose I use something like this. Now I will take a different perspective. This is x, this is y, of course z is pointing towards you, right. What happens if I take this plane? Right. So, what will x be? Minus y minus x. X will become y, right? X will become y, and what will y become? Of course, y will become x. In that case, what is the matrix? If this becomes something like this, yx, what is the matrix then? 0 1, what is the character? 0. What is the character here? Still 0, right. So, that is the meaning of this 0 here. If it was a 1D representation, it could never have been 0. Dipti, question. How it is 0? Do we agree on the matrices, right? What is the character? Character is sum of the diagonal elements, isn't it? So, here 1 minus 1 is 0 and here 0 plus 0 is 0, okay. Remember, it is this trace, not the other one, okay. So, see, if it was a one dimensional representation, you could never have a character of 0, right. As we said, it had to be either plus 1 or minus 1. But now we see 0 is possible if you have two dimensional representations. Why? Because these two dimensions are actually being mixed by that symmetry operation, okay. You cannot take them by themselves. So, depending on which plane you choose, either one remains the same, the other remains sign, or they interchange. That is how you get 0, that is the meaning of 0 here, okay. Now, another point to remember here, this is going to come very handy in our subsequent discussion, is that when two coordinates interchange, their contribution to the character is 0. Do you see that here? X and y got interchanged here, right, in the second case. So, the moment they get interchanged, what happens is that the non-zero elements go off diagonal, and that is why the character is 0. We will come back to this in a subsequent discussion later on. So, character here is 0. So, sigma v you can write any of these two matrices, it does not matter, 0 1 1 0, or you could write 1 0 0 1, 1 0 0 minus 1, and this is something that should make us appreciate the character table a little more. See, if you had to write the matrices, then I would have to write both the matrices here, right. In fact, I might have had to write more matrices, because if I took this plane for example, then what would it be? Then y would interchange with minus x would interchange with minus y. So, another matrix is possible. Even there the character is the same. This is the advantage of working with characters. It does not, you do not have to think anymore of what the matrix looks like. You do not have to think anymore of the basis, okay. The character is given and that is good enough, okay. Now let us work out C3. The C3 is something that we should be able to do, because we know the matrix for rotation by theta, Remember the matrix for rotation by theta, what was it? Cos theta minus sin theta cos theta, isn't it? So, what is cos theta here? What is theta for C3? 120 degrees. So, what is cos theta? Minus half. What is minus sin theta? Minus root 3 by 2. What is sin theta? Plus root 3 by 2. And what is cos theta again? Minus half. This is the transformation matrix. What is the character? This plus this, minus half, that gives you minus 1. So, this minus 1 that we see does not really have the same implication as the minus 1 that we see here. Even though the numbers are the same, the implications can be different depending on the dimensionality of the matrix. So, that is something that is important to understand. Numbers are same, right? This minus 1 just means that a function becomes minus of itself. That is not what it means here, okay. So, when it is 2 dimensional, this minus 1 means a little has a little more complicated meaning, and the meaning becomes apparent if you look at the matrix, alright. Now, some more character tables. This is before that, this is your, oh man, this is your C2V character table, this is C3V. Some other terms that you see are Rx, Ry, Rz. What is the meaning of Rx, Ry, Rz? Rotation with respect to x, rotation with respect to y, rotation with respect to z. Okay. Let us try and see if we can figure this out. Why Rx, Ry, Rz belong where they belong here. To do this, let me denote this, or at least let us do one, then we will understand. We will just do one, you can do the rest. If I write this as x, I write this as y, in which direction will z be? Which one is plus z, this or this? xy plus z points towards you. I keep forgetting this, I have never been able to overcome this shortcoming. So, I will draw Rx as a circle, circular arrow. Do you understand what this means? This is what it means, okay. Okay. Now, let us see where it should belong. When E operates on Rx, what do you get? You get Rx itself, no problem with that. So, character is 1. What is the next symmetry operation? Next symmetry operation is C2Z, this. Now, we have to be careful. What happens, this is Rx like this is your symmetry operation, or maybe let us do sigma v first, okay, let us do sigma v and sigma v dash first, that is easier. Let us apply sigma v. If you apply sigma v which is along the plane of the board, does Rx remain Rx or does it become minus Rx? This is a mirror plane, this is the direction of motion, what will the reflection, I will do it like this, this is a mirror plane, this is the direction of rotation, what will the image be? Like this, is that plus or minus? Minus, are we clear about this? This is the mirror plane, this is the direction of rotation, reflection of that will be like this. I can draw it, this is my mirror plane, which plane is this? The way we have formulated the problem so far, it is Zx. Right, Zx. So, x axis is somewhere here pointing out like this, this is the direction of rotation, what is the reflection? This, okay, and this, if this is Rx, this of course is minus Rx. Are we clear? So, for sigma v, the character is minus 1. What about sigma v dashed? What is sigma v dashed, remember? It is this plane. Please do not get confused. Now, I have interchanged the directions of the two planes. Now, this here is the molecular plane, okay. This plane of the board right now is your perpendicular plane. Now, what happens when this perpendicular plane of the board operates on Rx? You get back the same thing. So, character is +1. What I am trying to say is this, you have understood what Rx is, this is x, this is Rx. Now, of course, character of E is going to be 1, no issue with that. But if I now apply sigma v is Zx. Okay. Now, this time I will try another orientation. This is Z, this is X, this plane of the board now is your sigma v x. Okay. What is Rx? How did we draw it? Something like this. What will be the reflection on the plane of the board? Something like this. The important thing to understand is that the plane containing these two segments of circles is perpendicular to the board. Okay. Is that not Rx? This was going like this and the reflection is going like this. The sense is reversed. So, character is -1. Okay. Are we okay with sigma v now? What about sigma v dashed? Now, if I draw sigma v dashed like this, what will happen? It was rotating in this direction, it will still rotate in this direction. So, character is +1. What about C2? What about C2? This is your z axis, this is C2. If you now think of this Rx curled arrow, if you turn it by 180 degrees, where will it go? It will go, first of all, this one is above the board, right, it is on our side of the board. When you turn it, it will go behind the board, okay. But the tail will remain at the top, the head will remain at the bottom. So, it will be something like this. Isn't that minus Rx, right? So, character of that is -1. 1 minus 1 minus 1 1, where does it belong? 1 minus 1 minus 1 1, Rx is B2. Okay. This way you should try to work out Ry and Rz, and then this is a little more tricky. Here in C3V the problem is Rx and Ry jointly form the basis of a two-dimensional representation. So, if you can work that out, then you have really understood and then you have really developed the vision that is required to understand symmetry. Okay. Give it a try, it will work out. In any case, for our purpose, your character table will be given to you, you will not be required to derive it. Okay. So much for, so now we have learned what is there in a character table, right. Generally here the place that I have left blank, this is where we write the name of the symmetry point group. The top row contains the symmetry operations, the first column contains the molecular nomenclature, this segment contains all the characters, and then in the last two columns, the second last column contains x, y, z, Rx, Ry, Rz, the last column contains the quadratic terms x square, y square, z square, x, y, y, z, z x. Sometimes you can see things like x square minus y square and all, that depends on the character, that depends on the symmetry point group that you are dealing with. So, what I request is please have a look at D6H for example. D6H is the symmetry point group of which one? Benzene, right. See, this here is the character table for C3H. First thing to note is you have A dash, E dash, A double dash, E double dash. What do these dash and double dash denote? Symmetric and antisymmetric with respect to the horizontal plane sigma h. Second point to note is we have this scary E star, right. What is E here? Exponential 2 pi I by 3, which tells you that characters can actually be complex. Okay. In this course, we are not going to deal with complex characters. In case you study the course on group theory later on, that is where we will talk about this at length. Next is D6H is what I wanted to show you. D6H. What is the claim to fame of D6H? Why are we talking about D6H all of a sudden? Because D6H is the symmetry point group of a molecule that is an all time favorite with chemists, especially organic chemists. Which molecule? Benzene, right. Benzene is D6H, and in this course we are going to talk about electronic spectroscopy of benzene. We are going to need this character table there. Now, the reason why I am showing you this is that, see, there is sigma H or not, there is sigma H, but you might notice that this dashed and double dashed have been omitted. Why? Because if you just write this 1, 2 and GU, then your symmetry species are all defined uniquely. There is no need of dash or double dash. That is why it is not written. Okay? There is nothing wrong if you incorporate dash and double dash in the molecular nomenclature of these irreducible representations, but it is not necessary. Okay? Right. That brings us to the end of this discussion. We will now proceed to talk about wave functions as basis.